Okay, thank you very much, Emily, for your kind introduction. And today we'll explore climate smart switchgrass production and its role in sustainable agriculture and bioenergy systems. Now, a couple of weeks ago, DK gave an overview of this particular project that I will be talking about. And today I'll be discussing some of our results and that we think they imply in terms of climate smart switchgrass for bioenergy production. My presentation will follow this outline. First, we'll discuss what is climate smart switchgrass production, understanding its role in land management and sustainable biofuel production. And next, we'll dive into the components of climate smart agriculture using examples from our research. And we'll start with the productivity aspect, yield and profitability, assessing whether switchgrass can be economically viable, especially on marginal lands, and comparing it to profitability to traditional crops like corn and soybean. And then we'll discuss the adaptation, building resilience, and greenhouse gas emissions mitigation, and examining how switchgrass supports ecosystem services like carbon dioxide and nitrous oxide emissions reduction, carbon sequestration, and nitrate leaching reduction potential. And by the end, I hope to show how switchgrass can be a practical climate smart solution, balancing both economic viability and also environmental benefits. As an introduction to the concept of climate smart agriculture, is that we know that farming has negatively impacted by climate change. And at the same time, greenhouse gas emissions from farming have made climate change worse. So climate smart agriculture is seen as a way for farmers to address these twin problems while still maintaining yields and farm profitability. And today, climate smart agriculture is guided by three main goals, which are sometimes called the pillars of climate smart agriculture. And these are increased productivity by sustainably intensifying agriculture and enhanced resilience and adapting to climate change. And the third one is reducing or mitigating greenhouse gas emissions. Now, when we look at switchgrass production through the climate smart lens, we see a range of outcomes that drive sustainability and efficiency. And the first one is the productivity side. And the goal is clear here, is that enhancing yields and reducing costs. And this isn't just about growing more, it's about making production more efficient and profitable for farmers and stakeholders alike. And then we have the adaptation and resilience. And here we focus on strengthening ecosystems, improving soil health and increasing biodiversity, reducing water use, enhancing water use efficiency, and also ensuring better water quality. And finally, the mitigation component, and this is where switchgrass plays a powerful role in carbon sequestration, boosting both soil organic carbon, plant biomass carbon, and as well as reducing greenhouse gas emissions, whether it is CO2, N2O, and methane emissions, wherever possible. And here the point I also want to make is that though not explicitly labeled as climate smart, this concept is also well reflected in the objectives of the Sustainable Aviation Fuel Roadmap. And these objectives focus on expanding sustainable aviation fuel supply and end use while reducing costs, which aligns with the productivity component of climate smart agriculture. And additionally, SAF roadmap also aims to enhance sustainability by lowering carbon intensity through the value chain, which addresses the both adaptation and mitigation aspects of climate smart agriculture. So the vision behind climate smart switchgrass production is to create multifunctional landscapes. And these are systems that are not only enhance productivity, but also deliver valuable ecosystem services. And here, land management is planned so that switchgrass production is focused on marginal land, while most productive land or prime land continue to support commodity crops. And when we talk about marginal land in this context, in the context of climate switchgrass production, we are referring to land that is unsuitable for food production, of lower quality, or simply not economically viable for traditional cropping. And this land may be considered marginal for a variety of reasons, and including some might be small or regularly shaped, making large-scale row cropping inefficient, and others might have biophysical limitations, including being shallow or infertile soils, or having high erosion risks or poor drainage. And so beyond these physical characteristics, there's also the production-based definition of marginal land. And this is land where corn yields fall at least 25% below the county average. And by targeting these areas for switchgrass production, we aim to transform underutilized land into valuable resources that not only produce biomass feedstock, but also deliver critical ecosystem services, including reducing nitrate leaching, mitigating greenhouse gas emissions, and also carbon sequestration. So let's begin with the productivity and profitability aspect of switchgrass production. And as I mentioned earlier, one way to define marginal land is land where cost-effective production of commodity crops like corn and soybean is simply not viable. And to explore this, we compare profitability at field scale, evaluating how corn and soybean production stacks up against switchgrass on land that can be considered marginal within a farmer's field in southern Illinois. So now this land has a historical corn yield of around 123 bushels per acre, which is below the county average of around 200 bushels per acre. And the soybean yields here are of about 40 bushels per acre, which is way below the county average for around 60 bushels per acre. And it has also drainage limitations and also erosion problems and can therefore be referred to as marginal land. And in this analysis, we examine the relationship between net income and switchgrass dry matter yield in comparison to corn and soybean. And here on the x-axis, switchgrass dry matter yield, and here on the x-axis, dry matter yield required to achieve a given yield of income. And the green line shows the current realistic biomass yield at field scale, which is around 4.5 tons per acre. The blue, red, and black lines are farm gate prices of switchgrass that are used in the billion ton report, and these correspond to the $40, $60, and $80 per ton in English units. And so this graph shows that at current yields, switchgrass was not profitable in a continuous corn scenario at prices above $60 per ton. It is, however, not more profitable than corn and soybean or continuous corn at that price. And if you look at the price of $40 per ton, switchgrass is currently not profitable against any crop and may need more than 40% yield increase to compete with corn. At current production prices need to be more than $80 per ton to compete with corn and soybean production. And the main point here is that at the current switchgrass yield levels, land cannot be considered economically marginal and therefore suitable for transitioning from switchgrass only when replacing corn at $60 per acre or replacing corn and soybean rotation and have to be at least $80 per ton. So in this analysis, we assess the profitability of switchgrass across the state, identifying how much land could technically and profitably be allocated to switchgrass production. And to do this, we used expected corn and soybean yields based on soil productivity index and compared them to switchgrass production. Now, the figure on the left illustrates profitability in dollars per hectare at three different farm gate prices from the billion ton report. Green areas indicate regions where switchgrass is less profitable than corn and soybean. And orange and brown areas highlight locations where switchgrass profits are comparable to or exceed those of corn and soybean. And at $40 and $60 per ton, very little land can profitably transition to switchgrass if the original land use is continuous corn. And it's only at $80 per ton that parts of southern Illinois become more profitable for switchgrass and corn. Now, we see a similar pattern with continuous soybean, although in this case, even less land can realistically be converted to switchgrass. Now, the middle graph illustrates the proportion of land that can transition to switchgrass at different prices. And the land classifications, which is A, B, C, and 9 prime land, which has got soil productivity index of less than 100, are SPI index ratings. So for corn, only land below class C becomes viable for switchgrass and only at $80 per ton. And for soybean, only non-prime land, which is below 100 SPI, includes soil with poor drainage and erosion can realistically be converted. Now, Of course, there are always concerns about the food supply impacts on switchgrass when switchgrass replaces commodity crops. And the table on the right provides a quick analysis comparing corn ending stocks to the yield loss from potential switchgrass conversion. And looking at the 2018 to 2019 ending stocks, we see that switchgrass production will not significantly impact corn supply, except at the $80 per ton farm gate price, where ending stocks fall below the production decrease. And this analysis basically helps us to understand the economic and land use trade-offs, ensuring that bioenergy remains both profitable and sustainable. Now that we've established that switchgrass may not yet be competitive at the current yield levels and market prices, it is important to also consider the role of ecosystem services in promoting its widespread adoption. And to better understand these benefits, we compare switchgrass to corn as a reference crop. The first key point is that switchgrass provides ecosystem services due to both its biological characteristics and also management practices. And it differs from corn in three major ways, and one of them is the nitrogen requirements. Switchgrass requires far less nitrogen than corn, with the optimal rates of switchgrass ranging between 50 to 100 pounds per acre, while corn typically needs around 180 to 200 pounds per acre. Now, this lower fertilizer demand reduces input costs and also minimizes nitrogen runoff and greenhouse gas emissions, as we shall see later on in the coming slides. The second point is that above ground biomass management, where we are using best management practices for corn, is often a situation where crop residues are often left in the field and enriching soil organic matter. And in contrast, we need to harvest switchgrass biomass as bioenergy feedstock. And third is that the investment in below ground biomass, unlike corn, switchgrass allocates much more resources to its root system. And this deep root system enhances stabilization, carbon sequestration, and water regulation, and a whole host of other ecosystem services. And by leveraging these ecosystem services, switchgrass can become an attractive option, not just for biomass production, but also as a climate smart solution for improving soil and environment. So here we shift our focus to ecosystem services and beginning with greenhouse gas emissions. These results come from our current switchgrass experiments, all conducted at field-scale plots of approximately 1 acre. And our findings show that over 3 years, nitrous oxide emissions from switchgrass were between 20 to 50% lower, lower than those from corn. And the primary reason for this is the difference in nitrogen requirements. As I mentioned, at the best management practices, corn requires around 180 pounds, while switchgrass is around 50 pounds. And so this is a significantly lower input, and this translates to corn losing around not more than 2.5% of its applied nitrogen, while switchgrass loses around 8.8%. And so the key takeaway here is that most of the nitrous oxide mitigation from switchgrass comes from avoided emission, and this is simply because it requires less fertilizer. However, we also believe that switchgrass extensive root systems plays at least some role by uptaking more of the available soil nitrogen, although to what extent we still do not know. Another crucial point is that most of the emissions come from a few hotspot moments, typically right after fertilizer application or heavy rainfall. And so capturing these peak events is essential for accurately measuring the greenhouse gas mitigation potential of switchgrass and making informed management decisions to further reduce greenhouse gas emissions. Now, we look at CO2 emissions, and the story is a bit different. And the graphs here represent data from 4 sites across the Midwest, and a clear pattern emerges. CO2 emissions are higher under switchgrass compared to corn, and in fact, we observe almost 50% increase in CO2 emissions from switchgrass fields. And we believe this is primarily driven by root-associated respiration due to switchgrass having larger and more extensive root system. This pattern becomes even clearer when you're looking at the establishment here. In the first year, CO2 emissions from switchgrass and corn are almost identical, likely because the switchgrass roots are still developing. However, in the subsequent years, as the switchgrass rooting system becomes fully established, we see a notable rise in autotrophic respiration, leading to higher CO2 emissions. And this suggests that while switchgrass does release more CO2 emissions, much of it is linked to its active rooting system, which also contributes to long-term carbon sequestrations in the soil. And to confirm this, the increase in CO2 emissions under switchgrass is due to root-associated respiration. We conducted a targeted experiment using deep root exposure chambers. And these chambers are designed to block out root respiration, allowing us to isolate CO2 emissions from soil heterotrophic respiration alone. We also measured CO2 emissions from shallow chambers, which capture both the root respiration and also heterotrophic respiration. And by comparing the two, we could estimate the proportion of CO2 emissions specifically coming from root respiration. And the graph on the right presents some of our results from last year. And as expected, we found root-associated respiration accounts for almost 50 to 60% the total CO2 emitted from switchgrass field. And this confirms that the higher CO2 emissions under switchgrass are largely due to the extensive root systems, reinforcing the idea that switchgrass is not just emitting CO2, but also actively sucking carbon through its deep-rooted biomass. Now, since we know that increased CO2 emissions under switchgrass may be linked to greater root production and below-ground biomass, we set out to measure how much carbon is actually stored below ground. And these results come from our energy farm at Urbana, where we compared root production in corn versus production in switchgrass. And the key takeaway is this: switchgrass produces up to 20 megagrams of roots per hectare, and this leads to around 7 to 10 megagrams of carbon stored per hectare below ground biomass. Now, in contrast, corn only stores around 2 megagrams of carbon per hectare, a significantly lower amount. However, we found that a substantial portion of this carbon is concentrated in the top 0 to 30 centimeters of the profile. Now, naturally, we also hope that to see an increase in soil organic carbon under switchgrass, but our tests showed that no significant difference in SOC levels between corn and switchgrass. And this is not surprising, since soil carbon accumulation is a very slow process and often occurs in decadal timescales. And our conclusion, therefore, is that below-ground biomass carbon in switchgrass presents a strong short-term potential for carbon sequestration and offers a valuable demonstration of carbon storage benefits in switchgrass production systems, even before long-term soil carbon changes become evident. And here I present additional results on below-ground biomass production from the other trial sites. And these graphs above compare above-ground biomass production, below-ground biomass of switchgrass and corn. And what stands out is that switchgrass has much higher below-ground to above-ground biomass ratio, and this ranges from 1.5 to around 4.5, whereas corn remains below around 1. And so this reinforces the idea that switchgrass invests heavily in its rooting system, contributing to long-term storage. And a key takeaway here is that improved switchgrass cultivars may offer greater potential for below-ground biomass carbon storage compared to traditional cultivars. And some of these improved cultivars we studied include Independence and Liberty, and Carthage in South Dakota. And the most interesting thing is that in South Dakota, we saw higher levels of below-ground biomass with Carthage. And we believe the reason for this is likely due to the slower decomposition rates in this region's soils, which have got very high pH levels. And these high pH levels and also the much colder environment may inhibit microbial activity, leading to slower root decomposition and turnover, and thereby enhancing longer-term carbon storage. And so, in a nutshell, these findings suggest that soil conditions and cultivar selections might play a significant role in maximizing below-ground carbon sequestration in switchgrass systems.
Hey, Nictor, just a couple clarifying points on that slide. How old were these stands?
So these stands were at least 4 years old, at most 4 years old. Most of them, like the one in Urbana, was around 3.5 years old.
Okay, so technically mature. This is not first year growth for any of these locations.
No,
right?
the youngest stand was the stand in Urbana, which was established around 2020.
Okay.
The rest of them were around 2019.
Great. And then in the bottom right bullet, I don't know if it's a typo, but could you clarify what it says below ground biomass to below ground biomass.
Sorry, that's
Can you
a typo.
clarify which way you want that to go?
So I meant it to be below ground biomass to above ground biomass. I think that's a typo. I'm sorry for that.
Okay, so the newer
below
types,
ground to above ground, yeah.
So just let me clarify that the newer types have more biomass below ground than above ground compared to the older types?
Yes, they have the ratio of below ground biomass to above ground biomass is higher in the newer cultivars compared to the older cultivars.
Despite greater above ground yields in the new types. Okay, thanks.
And so these results highlight the distribution of carbon in below ground biomass across 4 locations, comparing switchgrass to carbon and once again corn. And once again, we found that carbon accumulation is highest in the 0 to 30 centimeter depth, which is expected given the concentration of root biomass in this layer. Now, ideally, we want more carbon stored deeper in the soil profile, as deeper roots decompose more slowly, ensuring long-term carbon retention. The slower decomposition rate at greater depths makes this carbon more stable and resistant to loss over time. Now, that said, even though most of the root biomass is in upper soil layers, switchgrass still develops deeper roots than corn, which is a positive outcome for carbon sequestration and soil resilience. This deeper rooting system also contributes to improved water infiltration and nutrient cycling, and also improves soil structure, which are both benefits of switchgrass as climate smart crop. Now here we examine carbon to nitrogen ratio of below ground biomass, which is an important factor in understanding decomposition rates and the carbon stability in the soil. And so the CN ratio serves as a key indicator of how quickly root material will break down. The lower the ratio, the faster the decomposition. And one clear trend we see is that corn has a lower CN ratio across all sites, meaning corn roots decompose more quickly than switchgrass. Another important observation is that the CN ratios increase as we go down the soil profile. And this suggests that organic material at greater depths decompose much more slowly, reinforcing the idea that deep-rooted carbon is more stable and long-lasting, which is exactly what we want to store carbon for longer-term sequestration. Now, however, the high CN ratio also has got implications in terms of nutrient cycling, particularly for nitrogen. With the slower decomposition, nitrogen is retained in the system, but becomes less available to plants. And this explains why soils under perennials may have high total nitrogen, yet much of it is not readily accessible for plant uptake. And as a result, additional nitrogen input are often needed to maximize switchgrass biomass yield. And so these findings highlight the trade-offs in cropping systems. Where switchgrass excels at carbon storage and soil stabilization, strategic nitrogen management is still necessary to optimize productivity. And lastly, we present the results of nitrate leaching reduction potential in switchgrass. And on the left, the graph shows nitrate leaching during the growing season, tracked over 3 years from the establishment year to the 3rd year. And one key finding is that in the establishment year, nitrate leaching rates were similar between switchgrass and corn, even though no nitrogen was applied in the switchgrass plots. And we believe this is due to the higher organic matter content of these soils, which promotes mineralization and nitrate release, leading to similar leaching rates in both crops. Now, however, over time, nitrate leaching decreased significantly in the switchgrass, and by the third year, we observed an almost 80% reduction in nitrate leaching compared to corn. And this is likely due to switchgrass extensive systems, which, as it becomes more established, is able to uptake more of the available nitrogen, preventing it from being lost to leaching. And on the right, we see nutrient removal capacity of different switchgrass cultivars, with the nitrogen removals ranging between 20 to 35 milligrams of nitrogen per hectare. And improved cultivars show higher nitrogen removal compared to traditional forage type cultivars like Shawnee. And this is mainly due to higher biomass yields. And it is important to note that biomass yield drives nitrogen removal, which explains that the lower nitrogen removal rates in the first year, since biomass yields is initially low and increases as switchgrass matures. Similarly, you'll notice lower removals rates in 2022, and this is likely due to the drought impact on biomass yield that year. And so these findings highlight switchgrass potentials as a climate-smart crop, not only reducing nitrate leaching over time, but also enhancing nitrogen uptake and efficiency in particularly high-yielding cultivars. And so to sum up our results is that overall, our findings highlight the significant environmental and agronomic benefits of switchgrass, from reducing nitrate leaching and greenhouse gas emissions to enhancing below-ground carbon storage. And while challenges remain, particularly in terms of the market competitiveness of nitrogen management, the potential for long-term sustainability and ecosystem services makes switchgrass a valuable option in climate-smart agriculture. And I think that was my last slide. And with that, I think I'll wrap up and I look forward to your questions and stroke comments.
Thanks, Nictor. That was fantastic. And again, that was just a small subset of Nictor's PhD work. And so I anticipate we'll have him back hopefully next fall to tell us about some Miscanthus work that he's done too. I had a question to kick us off related to that last nutrient removal slide. And then there's some questions coming through in the chat that we'll get to. So this one, were all of these, are these data corrected for a common harvest time, or how do you deal with harvest time as a variant when you're looking at when nutrients are removed? These are all post-senescence, but I can't help but look at that Iowa data in 2021 as being sort of anomalous.
Yeah, I think we try to have our harvesting timings almost synchronized post-senescence. And I know these represent lower removals if you're harvesting post-senescence. But it's almost like a trade-off, because if you want to have highest removal rates, then you have to harvest in the summer. But then this presents challenges in terms of the stand persistence. So how long do you want to wait until you replant your switchgrass again? So it's sort of like a trade-off.
Thanks. I'll just ask Andy's question since he's doesn't have his camera on, but can you clarify how rhizomes fit into your below ground biomass data for switchgrass?
Yeah, so that's one of the biggest challenges we had when we were trying to sample for the switchgrass below ground biomass. So in this data set, we did not separate the roots from the rhizomes, which I know we should, but then we had so much data and very little time to process that data. So, and that is why I make a deliberate effort to only refer to it as below ground biomass instead of just the roots, because we know the roots are going to be much less compared to the overall rhizome biomass. And we also think it's the main reason why, if you look at the top 0 to 20 centimeters of the soil profile, of the biomass profile, we see very high rates of nitrogen compared to what you would normally expect from a typical roots-only system, where nitrogen levels are actually lower.
Thanks. And one more clarifying question. Was nitrogen applied each year in these studies that you described today?
Now, so this particular project was designed to device-based management practices for switchgrass production. And so typically we don't apply nitrogen in the first year. And that is why, like I said, we still noticed very high nitrate leaching rates in the first year, despite no nitrogen being applied in those switchgrass plots. And that, like I said, is because of the very high organic matter levels in these soils. So the first year we did not apply any nitrogen, but all the subsequent years we applied nitrogen at around 50 pounds per acre.
Thanks. And I'll just encourage anyone with questions, go ahead and unmute and ask, or raise your hand, or use the chat. We'll get to any of those methods.
Well, my silence in part is there's so much data. I want to go back through it and look, kind of study it. So it's a true data dump, sort of.
There's definitely a lot here. In 2 weeks, we'll hear from Bill talking about, commercial activities with switchgrass in Iowa. So maybe we could revisit some of those financial slides from the beginning, Nictor. I think that's really exciting. Oh, and I guess I should ask you to give a plug about papers that you might have in review, or papers where we should go to look for this information other than your Google Scholar profile after the presentation. So for the YouTube audience, where should we look for this information?
I think most of the information can be found in DK's Lead Sustainable lab. Some of the economics data, which one of my lab mates is working on, is not yet on there. He has already published one paper on economics, focusing on the harvest logistics and how this impact greenhouse gas emissions. That's a recently published paper. We are also trying to finalize the last batch of papers focusing on production across sites and how much theoretical ethanol yield you expect from these cultivars, advanced cultivars.
Okay, then let's thank Nictor again. Thanks, Nictor. And we appreciate you doing this today, and we'll look forward to hearing more from you in the future. I'm going to put the IC YouTube channel website in the chat one more time. You can find Nictor's archived webinar here. DK's has 59 views, so Nictor, you'll have to see if you can beat that.